Good morning. So far what we have seen is that in machine vision we have different steps, and starting from image acquisition, in which we saw different type of cameras which are used for image acquisition. Then we went on to look at the relationship between the image coordinates and the world coordinates. Okay, and we saw here that using the 4x4 matrices, homogeneous transformation matrices, we found actually not a non-linear transformation called the perspective or imaging transformation, right. So we looked at P. Then we moved on to look at some basic concepts, and in this we saw the concept of neighborhood, distance, connectivity, etc. Right. Okay. Then we started to look at image processing, and basically we saw two different ways of doing it, which is the space based or spatial domain and frequency domain. Okay, these two types of methods we talked about, gave an overview on these, and then we started to look at the spatial domain techniques, and there we started out by looking at smoothing, right, under which we saw different type of averaging and including binary images. So the smoothing of gray level and binary. What we will start looking at today is what is called enhancement. Okay. Enhancement essentially means that you are going to take care of some errors which are not random in nature. Okay. Smoothing or noise reduction is basically for random type of errors where you could, I mean, it had some zero mean or regular distribution or some distribution, and then we want to get rid of that noise or eliminate or reduce it. In enhancement, we are going to look at techniques which are going to help us to see the picture a little better. Now there is a lot of subjectivity involved when we look at an image. In the image, what will appear as a good image to one person is not necessarily going to be agreed upon by everyone. When you look at these filters and the result of image processing filters, you will find that some of these will have some amount of subjectivity, but things like if you have a variation of intense light falling on this paper, supposing I look at this particular paper that is in front of you, so then if there is non-uniformity of light, then even if the object is uniform in its properties, reflective properties, you will have different shades of gray coming from different part of the same surface, although the distance from the viewer may be the same, right. So in that case you want to make sure that that appears as the same, right. So you could do some kind of corrective action. So one of the basic ways in which we do enhancement is by looking at histogram. Okay. In histogram, basically we are talking about, if I look at some intensity level, okay, I take some intensity level, how many pixels are there at that particular intensity level. So if I do the full mapping of that at this intensity level, we have so many pixels, So these are number of pixels and this is the intensity level. So then I will be able to plot something depending on what the picture contains, and I will get some kind of a plot like this, or I can show this as a histogram. At each of these intensity level I have some number of pixels corresponding to that. So that is basically how we will define the image histogram. Depending on how many levels of gray you have, you will have a histogram of something of this sort. Now if this is basically low intensity or darker areas and this is light, then here it is very clear that you have some histogram in which there are more pixels which are dark than there are light. Okay. So this is some kind of a darkish kind of image. If you take another image, you may have some other histogram for that, and then this will be generally a bright image. Okay. So histograms can tell us a lot of things, and in particular if you have a histogram which is having intensities, your full range is let us say from 0 to 255 intensity levels, but most of your picture data is contained in very narrow band of intensities, right. Sometimes this is, it is not easy to decipher details when you have a picture like this. So enhancement can help you here. So enhancement essentially deals with the transformation that we have talked about earlier, that if you have R as the pixels of the original image, then we apply some kind of rule to that and we find out what the new pixel intensities are. So these are intensity transformation. For example, if we have a image like this, perhaps it is better to take this frequency, this intensity level, and take these pixels and show them here, and take this intensity level and show it somewhere here, and so on and so forth, so that you can actually spread this out. So if I do all that, then perhaps my picture will look something like this. I have spread out all the intensities, so now I have very bright and very dark pixels, so the image has better contrast compared to a picture which has got very few levels of gray, which means everything looks the same gray level and details are hard to see. Okay. So now what we will do is we will look at this transformation and we will try to normalize this particular transformation. So supposing, now let me, in continuous domain, R is a continuous variable of intensities in the original image, then what I have shown you as histograms can also be shown as probability density functions, right. Instead of discrete values, one can have, if you have continuous curve like this, that again means that this is basically a darkish kind of picture versus a picture like this, which is going to be brightish kind of. So this is now in continuous domain, continuous intensity, okay, and then your histogram becomes a probability density function. Okay, probability density function. So what I would like to do is to normalize this and say that my intensity variables are, 0 is less than or equal to R is less than or equal to 1. So if I have 0 to 255 as the image intensity levels, I will say, okay, let me divide it by 255, so that you start from 0 and you get 1 as the maximum intensity corresponding to white areas. Similarly, I will say the transformed image should also have the same range of intensities. Moreover, if the transformation is such that, So now let me look at how the transformation may look like. So if I have R here and S here, then as I mentioned in the last lecture, if I have a straight line like this is 0 1 0 1, then that transformation does not do anything. It just takes whatever the input image is, output image is the same, there is no change. However, if there is some variation here, some other deviation from the straight line, then it is going to transform the image in some fashion. Okay, and so I am going to look at transformations which are going to be monotonic in nature. Okay, so let T be monotonically increasing function, right. If I do that, then there is a unique value corresponding to, unique value will come if I also assume that it is a single valued function. Okay, so monotonically increasing function and also single valued. Okay, so if I have a single value corresponding to for each input I have a single output value, then it is possible for me to define a inverse transformation also, right. That is, so if this property is satisfied, then okay, if this is so, then T inverse exists. Okay, this will be useful for us in doing some enhancement techniques. Okay, so let me look at the first technique, which I will call histogram equalization. Idea of this I have already given you when I said that if I have a very narrow band picture, then if I want to spread it out to cover most of the intensities, then I am doing it some kind of equalization of histogram. So here let us consider this transformation, which has the properties that I have already mentioned, and therefore I should be able to also write R is equal to T inverse of S. Okay. Now what I want is, if we have some probability density function for R, okay, so let me, this is my PDF of input image or original image, then I am saying this is some probability as a function of the intensity, right. Whatever the transformation is, it's going to now lead to some probability density function for the output image, which I will say P sub S as a function of S, where S is the intensity of the output image, and it will have some other shape, okay, whatever the shape is. The relationship between these two probability densities can be established, and that is given by Ps of S is equal to PR of R, that means the input image, times dr ds evaluated at R equals to T inverse S. Okay. So this relates the two probability density functions, and your transformation is coming into picture here. So if I want equalization, what I want is that my probability density function of the output image should actually be a uniform distribution, that all intensities are at the same probability of occurring. So that can be done if I look at, if I consider now, supposing I am having this thing here. Now my basic idea is that I would like to cancel these off. So if I for somehow I can make ds dr equals to dr of R, right, then this and this will get cancelled off and I will get unity at all intensity values, and which is what I really want, right. So this only means that ds is PR of R dr, and I can integrate this to get S is equal to integral from 0 to R of R, or I can make it dummy W dW. Okay, and this is nothing but the transformation that I am looking for, right. If I do this, then I can see that I will get a transformation which is going to give me equalized histogram. Okay. Okay, so I think what we can do is we can look at an example, and let's make the example. So in this example, let's say we have a input image which has a probability density function like this. So I want the area to be unity, so I am going to have this from 0 to 1. So this is going to be maximum probability density, this thing would be going up to 2. So this is PR of R. This is the property of the input image. So that means this is basically a little darkish kind of image. Now I can describe this in analytical terms. So I can say that PR of R is nothing but 2 times 1 minus R. So that at R is equal to 0 I have the value 2, at R is equal to 1 I have the value 0, right. So what I am saying is my transformation that I am looking for is actually integral of over R 2 times 1 minus W dW, right. This is the cumulative probability density function. So that I can evaluate because I have the expression for the probability density function here. So I get I will get minus W 2 times, okay, 2 times W minus 2 times W squared over 2 from 0 to R, and that is nothing but minus R squared plus 2R. Right, this is my transformation that I have defined now, that if I take whatever input intensity R is and I find out the output intensity S, which is going to be relating to the original intensity like this, then I will be able to equalize the histogram. Okay, so this is what I am going to demonstrate now. So let us now reverse this equation so that we have the inverse transformation, and in the inverse transformation I will have R is given as 1 plus or minus square root of 1 minus S. Now we have to remember that R should vary from 0 to 1 only, therefore I have to basically take the minus sign, right. If I take the plus sign, then it is going to become more than 1. So in fact it should be 1 minus square root of 1 minus S, and therefore I can calculate the probability density function of the output image as PR R times yes, okay, evaluated at equals to T inverse S, which is equal to this. If I substitute, I have 2 times 1 minus R times R is given here 1 minus square root of 1 minus S ds, okay, evaluated at R, and that you can see that it comes out to be what I am looking for, which is I can substitute for R here also, and therefore I will get 1 minus S square root, and this, if I take the derivative, I will get the same here 1 over 2 1 minus s. So, this indeed will come out to be 1. So, the transformation that I have got now is basically r squared with a minus sign plus 2r. So, that is going to look like a parabola 1 0 0 1. This is nothing but s is equal to minus r squared plus 2r. Okay. And my output probability density function is going to be simply 0 to 1 1, it is 1 everywhere. This area obviously must be the same as this area, because we are not altering the total number of pixels. Of course, we can't talk about pixels, this is a uniform continuous domain description of the image, which is not going to be so, because we have discrete resolution of the camera. So, one can adapt this problem for discrete images. So, we can write discrete form of this. The probability density function now becomes the histogram, and that is nothing but the number of pixels of gray level k divided by the total number of pixels. So, this is now probability of a pixel being of gray level k. Okay. Gray level k is that rk, and this is the number of pixels, okay, belonging to gray level k, and this is nothing but total number of pixels. This is very straightforward. This is just saying that a whatever number of pixels I have in gray level 2 or 3, then divide by the total number of pixels, that will tell me the probability of a pixel being of that gray level, right. So, now if I look at the so histogram is nothing but a plot of, okay, it's a plot of ER RK versus RK, discrete intensities R1, R2, R3, etc., etc., Rn or Rn minus 1 starting from R0, and then whatever number of pixels I have in each of them is going to give me the the intensity histogram, whatever it may look like. Okay. So, what will be the, since we will be dealing with discrete numbers, we have to be able to see how we will do the equalization here. Okay. So, equalization, we have to find the transformation which is equivalent of integration, right. So, for integrating, the what we will have to do is to approximate it by a summation. So, if I do nj over n summation from 0 to k, that will give me sk, that is the transformed intensity values. So, this is nothing but my transformation from RK. Okay, I think the best thing to do is to look at an example, because that will illustrate how this technique will be used. So, we will look at now an example. That is right. So, you can think of it as a lookup table, that you have a given intensity level. Now, all pixels of that intensity level we are going to transform to some other intensity level in the output image, right. But what those intensity levels should be is how to figure it out is what we are looking at. If you want to equalize the image so that you have good distribution, you have roughly equal distribution of pixels in all different intensity levels. correct. That you can do, and in fact that is one of the techniques. So after looking at histogram equalization, we will look at histogram specification. Histogram specification precisely deals with that kind of a problem, but you will see that it is actually, once you understand equalization, specification will be just a slight extension of that. Okay, so let us take an example of some gray level image, and how do we describe the image? Let us have only limited number of gray levels, say 8 gray levels. So k going from 0, 1, 2, 3, 4, 5, 6, 7. Okay, now the intensity of this is going to be, let us say, uniformly between 0 and 1. So last one is going to be 7 over 7 or 1. Okay. Now depending on the image, the number of pixels in this intensity level will have to be counted from the picture. So let us say this is 790, this is 1023, this is 850, this is 656. Okay, then we come to 329, 245, 122, and finally 81. So this is our image. If you add it all up, it comes to 4096. So I am assuming it is image of 64 pixels by 64 pixels. That will give you 4096 total pixels. Okay, so now our probability or the histogram is going to be this nk divided by the total number of pixels, which is 4096. So one can compute that as 0.19, 0.25, 0.21, 0.16, 0.08, 0.06, 0.03, and 0.02. So we have now basically the histogram. And what I will also like to do is to find the cumulative sum nj by n going from 0 to k. So going from 0 to 0 is, I am going to have only one of them, which is this. Then the cumulative will become 0.44, 0.65, 0.81, 0.89, 0.95, 0.98, and 1.00. Okay. So this is defining for me the transformation. So now let me see how everything is looking. This is my input image, 0, 1, 2, 3, 4, 5, 6, 7. The values, the maximum value is 0.25. So divide that into 5 equal parts. 0.19 will come somewhere here. This is the first one. 0.25. Then we have 0.21. And then we have 0.16. 16 will be just above that. Then we have 0.08, which is half of that. Then we have 0.06, 0.3, and 0.2. So this is our histogram. If I show it, okay, this is my intensity histogram. The transformation is going to be defined by this, which is going to be simply, if I plot Rk versus Sk transformed image, and here I have to go from 1 to 1. So 8 divisions here, and okay, let's do 5 divisions here. Okay, so 0.19 is what I had here somewhere, then I have 0.44, so this will be somewhere here, then I have 0.65 which is going to be somewhere here, then I have 81 which brings it here, 89 which will be halfway down there, okay, then 95. Now it will be very difficult for me to draw, because so it will be some kind of a distribution, some kind of transformation like this. Okay. Now what I have to do is I have to ensure that my output image is equally distributed, right. So now if I divide this axis also in 7 or 8 different categories here, so I basically have 0, 1 by 7, 2 by 7 up to 7 by 7, 7 by 7 is here. So now I need lines here which is going to correspond to 1 by 7, okay, 2 by 7, and I am going to, I mean it will be difficult for me to retain accuracy here, but what let us look at the first few ones. So now look at the output histogram, and 0, 1 by 7, 2 by 7, let us look at those only. Okay. So now at 0 I have nothing, okay, 1 by 7 I have, this is the closest, this level here is closer to 1 by 7 than to 2 by 7. So here, because I am dealing with discrete numbers, I have to now choose between one or the other. Okay, in the continuous case we did not have this problem. So I have these many pixels must belong to 1 by 7. So those are corresponding to 790 pixels or 0.91 of the total. So this should have 0.19. Maybe supposing this is 0.2, this is 0.4, 0.6, and so on and so forth. Okay. Actually I had to, no, I should make my scale the same as this. So let us say this is 0.25, 0.20, 0.15, okay, 0.10, I think I missed out a line here, this is this, and 0.05 and 0. So now 0.19 is here. I hope it is clear. Let me otherwise draw a separate one a little more clearly. Okay. Okay, 0.20. I won't draw too many more. This is 1 by 7. This is 2 by 7, 3 by 7, 4 by 7, 5 by 7, 6 by 7, and 7 by 7. Okay, so what I am saying is that there is no pixels here. Now I have pixels which are all the first category pixels are 0 pixels have been transferred to S1 pixels. Okay. Now next one is 0.44, which is very close to 3 by 7. Okay. So 2 by 7 I have no pixels at all. Okay. 3 by 7 I will have all these pixels which will go there. So these pixels were 0.25. So I have in the output histogram I have all those pixels which were at the intensity 1 by 7 in the original image are now pixels with the intensity 3 by 7, which are in the fourth category of intensity. So you can see that it is not changing these pixels, the number of pixels in each category so far is the same, right. Of course we are pushing it this way because we had more pixels in the dark region here. Now we have to put more pixels in the lighter region. So we are going to, these are getting shifted appropriately, and you will see that some of these categories will get combined together. The last 3 categories will get combined together, the second last 2 categories will get combined together to give us a histogram which will have this. Next category will be 5 by 7, which will have 0.21. So 5 by 7 has 0.21. Then the next two categories combined, and that is 0.24. So this 6 by 7 is going to have 0.24, and last three categories here will get combined, and that is a total of 0.9 and 0.11. So 0.11 will be somewhere here. This is going to be the output histogram that I will be getting. No, not at 0, at 1, intensity level 1, because if you see 1/7, that is, it's close to 0.19 level. Okay. So this is we have done the same thing that we did for the continuous case, only now there are approximations and there are discrete. So the histogram doesn't look like a uniform values all for all the intensities, but in an average sense this peak is a little higher. So in the next pixels you don't have any intensity level, you don't have any pixels, and it is basically some kind of a equalization, and it will help to view the image better with this equalization. So before we move on, let us just quickly look at histogram specification. I will not go into details, you have already got an idea about histograms and how to deal with them. Specification. Okay, what we have seen is, supposing I look in continuous domain only, so I have one PRR of the original image. This is the PDF of the original image, and I have some desired PZZ of the PDF of the desired image, or the desired PDF of the image of the output image. Output image probability density function. Now what I will do is, I will just use what I have used so far. So I know that I can find a transformation which will take my input intensities and equalize it. So this is the transformation which is given as 0 to R PR W dW. Okay, this equalizes equalizes S. This is the output image of this particular transformation. Similarly, supposing I took the desired output image and I say, okay, can I equalize that also? So whatever specified PDF was there, I can find a transformation which is going to equalize that. So say that is V is equal to some G of Z, which is of course going to be defined in the same way, 0 to Z PZ W dW. Okay, so this equalizes my other image, which is the Z image, right? Now all I have to do is, if I equalize this and this image are the same actually, right, because both have the same distribution, which is the equal distribution of pixels in different intensities. So all I need to do is to find the inverse of this. So the procedure is going to be like this, that I will first use this, I will find this, and then I will use this in the reverse sense to get Z is equal to G inverse of V, which is nothing but S, because both are equalized, so it's the same. So this is going to do the job for me, or which is of course, so Z is equal to G inverse of T of R. Right, you get the logic behind this. So I have some probability density function which is of the image that is given to me. I am looking for a particular specified distribution or probability density function. I can equalize both, I know how to do that. In one, I go from input image to equalized image, then from equalized image I go by reverse transformation of the second probability density function, so that I will now end up with from equalized image to the specified histogram or probability density function. So this in each of these cases what I will do is in the next class I will give you some examples, because then it will become clearer to you what happens. Take an image, apply this type of histogram equalization, what happens, specify a particular histogram, then what do you get, and you will see that it makes a remarkable difference in terms of the way the picture appears to us. The information is not any additional information, but you will see that from just a gray looking picture with hardly any details that you can discern, you will start to see details when you enhance the picture. Z is the intensity, intensity variable of the output image, which is also going from 0 to 1. So it is the total intensity range. Okay. Now let us look at a few other enhancements. One important enhancement is making edges little more prominent, okay, making edges more prominent. Edges are usually at the boundary of two objects or two different regions of some different properties. So therefore if we can enhance them, we can clearly see different things in that, in the image. So edges are places where you have change of intensity. That is how you will determine edges, either change of color or change of intensity. So if you are talking about gray level only, color will make it easier, but if you look at only gray level, then we are talking about change in intensity. So that means we need to have some kind of estimation of gradient of the intensity. So gradient, if I define x gradient as del f del x, okay, which can be estimated to be f x y minus f x minus 1 y. Okay, this is the gradient in the x direction. Similarly, I can have a gradient in the y direction, which will be approximately f x y minus f x y minus 1. So we are looking at just a difference approximation for derivative. A better approximation is actually if I try in terms of masks, okay. So this here of course we were having a pixel p, I am only looking at, for the x1 I am looking at the previous pixel, and for the y direction I am looking at the previous pixel here. So I am looking at the difference between the intensities here as a measure of gradient. But a better, so this is plus 1 and this is minus 1, let us say for this. A better operator or a template is more robust. Supposing for the gy I want to find, so if I take minus 2 0 2 and minus 1 0 1 and minus 1 0 1. So what I am doing is I am finding out the gradients along the x value, and one value prior to x and one value after that x with respect to the pixel of interest, which is this p, right. So then it kind of averages the gradients just above, just below, and gives more weightage to the gradient at the in the middle. So this gives you a good estimate of the, this is the estimate for gy. You can write out the full thing if you want, but basically it will only be saying that this is nothing but fx plus 1, okay, this sorry fy plus 1 minus, so this will correspond to, so this approximation now is f, we are talking about x minus 1, right, y plus 1 minus f x minus 1 y minus 1, right. then I am talking about f, this is now x level, x y plus 1 2 times minus 2 times f x y minus 1 plus f x plus 1 y plus 1 minus f x plus 1 y minus 1, right. It's similar, but it's more robust calculation of that. Similarly, for the x gradient, I can say this is 1 2 1 0 0 0 minus 1 minus 2 minus 1. Okay, this is a very common mask which is used for finding gradients. It's called Sobel operator, Sobel mask or Sobel operator. Okay, so once you find, basically what is going to do is, if the image was uniform, then this mask will come out to be close to 0. If there is a change in intensity in the x direction, then this mask will give you a high value, y mask will not give you a high value. If on the other hand you have oblique line, then both of these masks will give reasonably high values. So after going through this mask, one can then say, okay, I can threshold, and I can say that g of xy in the output image is now going to be 1 or 0. 1 it will be if my gradient, okay, of original image is greater than some threshold value t, otherwise it is going to be 0. So then I will only pick out the pixels which are belonging to the edge, okay, and that will clean out the image a lot, because you may have a lot of details available in the image, but what you are interested in is basically regions, boundaries which are separating various regions. So if there is a hand and there is a background, you perhaps want to look at the hand, or you have a part, washer and a nut and bolt lying on the image, you want to look at the boundaries of this so that you can recognize a washer as a disc with a hole, okay, or some transformed or deformed version of that depending on the angle of vision. So those kind of things can be done using enhancing the edge and finally making it binary also. So I think we will end here, and we will look at higher level vision from in the next lecture.